It's much easier for me to talk in English. So I'm a Dutch American. My wife is Mexican American. Our common language is English, so that's the way it goes. However, so I'd like to share you my research that I've been doing at the University of Arizona, but quite often in collaboration with a lot of other institutes. And you can see a few there. I've been working with Universodad de Sonora, universities in Argentina, Chile, Global Change Institute, being funded by the Inter-American Institute for Global Change, and a lot of our funding comes from NASA as well. So I'll be talking a little bit about the experiences, giving a little bit of an overview. We're currently working on land use, land cover change, and water use in the Americas. AquaSec is one of the acronyms there. But today I'm going to talk a little bit about some research we did with Universodad de Sonora and some other work we're doing in some of the arid regions of the world. So just to give you a little bit of an overview of some of the work we're doing a lot of time series analysis. Time series analysis allowing us to do a lot of dynamics analysis about land cover and what's taking place in different parts of the world related to climate change, global variability, and things like that. So my main work focuses on natural resource and urban remote sensing monitoring and assessment. Been working quite all over the world, but focusing on arid lands quite often. Quite often also using multiple platforms. I mean, quite often the solutions to challenges and answering questions is related to actually multiple platforms. There's no one platform or sensor that allows us to solve a question or answer a question. So it's multi-sensor, multi-dynamics, temporal, spatial resolutions, and scales in effect there. Here you see a little bit of a view of what the average conditions are in terms of land surface response, where you have the vegetation response here in green for an area in Texas. You saw here the red line here, we had a big drought in 2011, and where you get below average conditions. So some of these satellites fly over every day, and it allows us to really use these data sets to look at the land surface responses in response to climate variability and change. Since I was coming here, I thought, oh, let me check it out and see what the atmosphere looks like from 1986 all the way to 2015. I took a Landsat look. It's a USGS resource, something everybody can get access to it. You can download data, you can look at data really quickly, and you can see some of the changes taking place, the urban area here in kind of gray, and you can see kind of the expansion taking place and different land use and things changing. And I'm not an expert here, but you definitely can see a lot of changes. And going from here most to the globe to another area here where there's another a tool from NASA. It's called Worldview. It actually allows you to look at data that's being collected about 4 hours ago to 24 hours ago, going back in time, basically daily data. So this was relatively recent, like a week ago. I think you had a clear day. And although I don't think you have too many clear days here, you have a lot of clouds. This is just a view of a worldview that allows you. So definitely take advantage of the resources that are available to you. I'm paying taxes in the US, so take advantage of the tax money that I pay and use these tools to your advantage. So these are all free, all the data are free, all these tools are freely available to you. So another resource is that there's many platforms and missions going on, and I just have a NASA perspective here, but there's many satellites out there that look at the ocean, the atmosphere, the land, and some of the satellites that that was talked about, you have heard about already. So I was a scientist on the MODIS sensor on the Terra platform, and that's what I'm using still. There's lots of other satellites here that look at oceans, atmospheres, and things like that. Again, a research for you to use to look at these different processes around the world, from atmosphere to ocean to land interactions. So, in terms of my talk, what I was going to talk a little bit about was from data to decision making, related to some of the work we're doing at the University of Arizona. So, quickly introducing some of the Earth system processes that I'm interested in, then an example of some collaborative work I did in South America, collaborative work in Sonora, and then some work we are doing to make these data available to the public. How am I doing? Am I going fast for the translators? Going good? All right. Is this working? So one of the things I'm interested in is the timing of land surface responses or vegetation growth. It's called phenology. Land surface phenology is about the timing or the biological clock around the world. And we can monitor that with satellite data because we have daily satellite data, and of course, if we have cloud-free data, we can see the Earth's surface. That phenology, that land surface response, is affecting a lot of global Earth systems processes, from water to carbon to animal life to people, right? It's just the timing of when things are taking place will affect your allergies, it will affect the monarch butterflies as they're migrating through Texas when it was a drought year. They didn't find the resources. So the timing of the land surface in terms of when things are growing, when you are affected by allergies, when mosquitoes are basically having a good habitat to be prosperous, basically, and infecting lots of people, those are the things that are related to phenology. It's that interaction of biology and the environment. So in terms of the Intergovernmental Panel of Climate Change, they really saw phenology as one of these things that are easily observable, a simple process. I'm not sure that's the truth, but climate change will affect the timing of different land surface responses. And it is related to all these things that you see: fruit ripening, plants, bird migration, things like that. Well, if things are out of sync or things are asynchronously flowering or migrating, then you have an asynchronous event, basically, that doesn't really end well for everybody, right? Quite often. So there's no resources, there's no happy ending for birds that don't find any food, or butterflies for that matter. But it affects people as well, in many different ways. So this is a seasonal animation of 1 year of MODIS NDVI data. NDVI is Normalized Difference Vegetation Index. That is basically a measure of the amount of vegetation that's on the Earth's surface. And you can see here how seasonal changes are taking place throughout the year. Kind of the lungs working on a global scale. What we take advantage of here is that satellites can observe the red reflectance and the near-infrared reflectance. There it is. So those two measurements basically are computed, and then NDVI gets computed after that. The NDVI then is related to the amount of vegetation in a lot of different vegetation types. So this is probably the most used index throughout the world, in the remote sensing world. It looks simple, but at the same time, taking advantage of that information that's in there is another issue. So I'll be going through some of that related to that. What you see here is the NDVI is a function of the amount of vegetation in terms of leaf area index. And you can see that the NDVI itself has many values for a particular LEI, and many LEI values have one NDVI value. So there's a lot of noise there. And you basically have to know the relationship for the NDVI and the land cover to actually derive information from it. All right, so phenology is about timing. So timing is about then deriving when things are greening up, and in this case you have the NDVI, the green cover basically, and you see here the seasonal patterns every year, basically greening up for a woody cover site in Arizona. And you basically have year one, 2001 to 2005. You can see there's a lot of noise in these data sets related to cloud cover and atmospheric effects and things like that. That's why we take the upper envelope to reduce kind of the cloud cover impacts. Now this is going to be fun, there's a lot of different arrows coming up here. To actually characterize 1 year, we actually want to know the start of the season, right? To derive when things are starting. We can do this for this particular point and location. So you have the start time and the NDVI value at that start of the growing season. At the same time, you have the end, then you have the peak, the length if you have the start and the end, the amplitude, basically the difference between the minimum and the maximum. You can do a derivative for basically the strength of the growing season. How fast does it green up? How fast does it brown down? And then at the end, that integrated surface under that curve is a measure of the amount of biomass that grew during that time period for that one particular year. And then that large integral, all under the curve, is then a measure for the total amount of biomass that's there. So these are all proxies for land surface responses that can be derived from time series, the daily data that you can get from the satellite data that is actually available to all of you as well. Now, what I also did is that quite often the winter-spring season versus the summer-fall season are quite different. So I kind of discriminated between those as well by integrating over time those areas as well. You can do that for one point, but if you want to do that for a whole image, you can actually do the same exercise for time series of images that are cloud-free. So we actually do a composite where we actually filter out the clouds and the minimize atmospheric conditions, basically. Look at the surface, stack of images for years and years of data, basically, that's out there. And then we actually can derive all of those points for these images in geographical format, basically, where you see here some of the timing variables, some of the amplitude, the amounts of vegetation that's growing there, and so forth. So I'll show you some results for South America, just one slide giving an overview of some published research where we looked at the bioclimatic response for South America. I was on sabbatical in Santiago, Chile, working with Francisco Mesa. And what we did there was to kind of look at what are the climate impacts on vegetation responses for South America. And besides all the both management and land use impacts as well, looked at some of the more arid regions of that area, knowing that Santiago and this area is undergoing more drought as we move forward. We also saw, when we looked at this, we took 30 years of AVHR, multiple sensors, we put all those 30 years of data together. For every 2 weeks, we took a snapshot of what was taking place, and then we looked at that in terms of how did that productivity and the timing of every year, how has that changed over those last 30 years? And we related that to El Nino and to the Antarctic oscillation indices to kind of saw what part of the continent was impacted by those climate indices. So we actually published that, so if you're interested, please read up on it. But that's basically the strength of these data sets that are maybe coarse, but they have temporal resolution that's very fine. It allows us to do these kind of studies on a global, in a global arena. So for Sonora, we were interested in similar things where there's a lot of changes going on in Sonora. So being from Tucson, Arizona, working with a colleague and a student that graduated from the University of Arizona, Raul Roma Leon. He's a professor there now in Universodad de Sonora. And we look at kind of the variability and change in that area related to agricultural changes, salinization of soils, and things like that that are taking place there. So these are a few slides related to looking at the timing of the Sonora region, looking at the variability and change, some of the causes that are causing these changes as well. So this is just an example of after deriving, having all this time series, you actually can then derive the start of the season based on the algorithm that I showed you before. It's called TimeSet by Johnson and Eklund. It's freely available software if you want to use it. You basically can then derive, as you can see here, these are the day of the year 0 to 365, where there's a lot of start of the season taking place about May, June, and when the monsoons basically come in. You also can see at the same time that some of the Obregon region has a lot of agriculture. It doesn't really follow the precipitation patterns because it's all irrigated agriculture. Another example is the length of the season, where you see the desert environments are very variable. Some of the more higher elevation inland affected by, less affected by that variability, but quite long growing seasons and all variable all over that region. Some more examples where looking at, so this is MODIS data. First I talked about AVHR data, 1 kilometer resolution to 5 kilometer resolution. This is MODIS data, 250 meter resolution, and every 16 days you get a clear scene for that area. So I need to hurry up, I hear from my... All right, so some more examples then about, you can look at then interannual variability, where you look at the standard deviation over the mean and derive interannual variability. For this case, from 2000 to 2012, the time MODIS is available. It's still up and running, so we have 16 years of data. So I'm going to go through this relatively quick, where we can start looking at winter and spring seasons. Again, seeing some of the agriculture very different from some of the other areas. Same thing for the cumulative NDVI and indication of productivity. Again, the agricultural area very different from the surrounding. The different seasons, I'm not going to go into it since I'm running out of time. So now you can actually then start looking at this in time series and look at this productivity from year to year and actually start looking at trends. And we have decreased productivity in the red, we have increased productivity in the green, a lot of it related to different land uses in different parts of the region. So this to then, because we have so much data, we actually can start seeing what are the trends, when things are taking place, because we can actually drill through all of these data sets and look at every year and see when things are changing. So you can see here seasonal patterns, then more intense agriculture, all of a sudden you get a decrease and then starting to increase again. So lots of information in these time series of these data sets. I'll show you a few more examples where there is variable agricultural production in these areas. Here you see agricultural areas that are changing their growing season patterns, where you have a single growing season versus here a bimodal or two growing seasons actually sometimes occurring. So different cropping patterns occurring in some of these areas, but overall an increase in productivity if you start looking at it. Another one example of bimodal and single growing seasons. So all of this data is readily available to characterize responses to different land uses and climate patterns. In this case, you see La Costa de Armacillo, where there's a lot of agricultural activity, but at the same time there's also what we can see here, agricultural abandonment, salinization, lack of water, changes in policies really changing land use patterns in La Costa de Armacillo. We know that also because we went to another scale besides looking at these kind of temporal scales, there's a lot of information over time, but still relatively coarse. Raul and I worked together on Landsat classifications and used Landsat to kind of see when things were changing, where they were changing in a 5-year interval, and basically seeing that a lot of aquaculture came in along the coast that you didn't see in 1988. Lots of fallow land. People can't really start using their land anymore, or they have to leave it aside for a while. So the last few slides. So making this kind of data available to the user communities and the stakeholders and decision makers, we can put this data into a decision-making framework. This is a website called droughtviewarizona.edu. It actually downloads the NASA data every day when it can. It processes it in a way that is relatively user-friendly and allows you to look at changes over time, but also the difference from average for the same time of the year in that particular area. So here you can see some above average conditions and below average conditions. So this is bi-weekly data. You put contextual information with it, and people start using it as an extra tool for decision making. It's not the only tool, it's just another line of evidence for people to use and see what's taking place in their environment, because you can zoom in basically pretty detailed to the pixel level to the area that you're interested in. So this website allows you to look at drought impacts in a core regional scale, but then also more zoomed in if you wanted to. So the last part is that the impact reporting you can start incorporating too, where people on the ground can take the smartphone, start actually using this data set, and then also their smartphone to locate when there's a drought impact or other impacts that they then can start using to report and create a database. So my last slide is to kind of show you that this requires a lot of training. It likes different organizations to take advantage of this. So the university has extension, education, and research going on, and these tools basically gets distributed based on an organizational structure that brings these data out to the public through extension, like John was doing. So I think this is finally the end. Lots of spatial temporal patterns you can observe relate to climate variability and change. You can analyze these things in terms of decision making. The two-way knowledge exchange is really important. We work with stakeholders and managers to really find out what they want, what kind of tool is important to them. So, thank you. Muchas gracias.